In this video, we're going to continue our discussion on limits and learn how to actually calculate limits algebraically using a variety of different techniques. So before we start evaluating our limits, let's first go over some limit laws that we're going to use either directly or indirectly quite a bit. So our limit laws first, we need to suppose that C is a constant. And we're also going to suppose that both the limit as x approaches a of the function f and the limit as x approaches a of the function g exist. Then we have a lot of different laws for our limits. The first one says that the limit as x approaches a of the function f plus or minus the function g is equal to the limit as x approaches a of f plus or minus the limit as x approaches a of g. So just in words, this is saying the limit of the sum is the sum of the limits, or the limit of the difference is the difference of the limits. This is a limit law that should feel pretty intuitive because it's how you would want things to work anyway. You would want this limit to work out so that you can take the limit of each piece separately and then add the results together. And it is true all the time. Our second limit law involves multiplying by a constant. So we have that's the limit as x approaches a of some constant times a function is equal to the constant times the limit as x approaches a of the function. This is another law that works just the way you'd want it to. If you're multiplying a function by just a constant number, you can take the limit of the constant times the function and find out that the result is the same thing as the limit of the function multiplied by the constant. Our third limit law says that the limit of a product of functions is equal to the product of the limits. So if you have two functions multiplying together and you want to find the limit of that product, you can find the limit of each function individually and then just multiply the results together and you get the same result. Limit law 4 involves the quotient of functions. The limit as x approaches a of f of x over g of x is equal to the quotient of the limits if the limit of g of x is not 0. So that last bit there is just making sure we're not dividing by 0. So if you have a quotient of functions that you need to find the limit of, as long as the function in the denominator does not have a limit of 0, you can find this limit by just taking the limit of the top and the limit of the bottom and do the ratio of those numbers. Limit law 5 involves powers. A limit as x approaches a of a function to the nth power is equal to the limit of the function to the nth power. And we're using positive n, which also happen to be integers, so positive whole numbers. So the limit of a power is the power of the limit. And our very last limit law to write down is very similar to that last one, but involves roots. So limit law 6. The limit as x approaches a of the nth root of a function is the same thing as the nth root of the limit. And again, we're going to use positive n and an integer, so a nice whole number. So the limit of a root is the root of the limits. All right, so now we're ready to actually do some examples. Our first few examples are going to be very straightforward, calculating limits. It's going to be your favorite type of limit, I'm sure, because all we have to do is just plug a number in and evaluate. So let's start with a few basic examples. First example, we're going to do the limit as x approaches 5 of 2x squared minus 3x plus 4. Now, based on all the limit laws that I just wrote down, I could split this up into 3 different limits, but honestly, the way I usually do it is I remember those limit laws in the back of my head and just think about applying it to each piece without actually rewriting it that way. So when you have a limit like this to calculate, the first thing that you should try to do is simply plug that number in for x, because if you actually get an answer that way, you're done, and it usually doesn't take too long to check that. So I would always try just direct substitution first. So let me plug that 5 in and just see what happens. I get 2 times 5 squared, which is 25 times 2, which is 50. Then I have a minus 15 and a plus 4. And when I do all of that addition, I get 39. So this limit is equal to 39. And remember, what this means is if I were to graph this function, if I get closer and closer to x equals 5 from both sides, my y value is going to get closer and closer to 39. Example 2. Let's find the limit as x approaches negative 2 of x to the third plus 2x squared minus 1, all divided by 5 minus 3x. So we have a quotient of functions here, and we know from our limit laws that the limit of the quotient is the quotient of the limits, provided we're not dividing by 0. So to evaluate this limit, I'm going to do that very first thing that we should always try, which is, again, just plug that number in and see if it works. So I'm going to plug in a negative 2 and see what happens. So plug in negative 2 for every single x. And let's see what happens. So on the top, I have a negative 8 and a positive 8 and a minus 1. And in the bottom, I have 5 and plus 6. So when I add these things together, I'm going to get a negative 1 on top and 11 on the bottom. My limit is negative 1/11. And again, this just means that if I were to graph this function and I get closer and closer to x equals -2 from both sides, the y value of this function is getting closer and closer to -1/11. Let's do one last example with direct substitution. And this example is going to involve some trig. So we have a limit as x approaches pi of x times cosine of x. So again, I'm just going to try to plug that pi in and see what happens. Now hopefully you're very comfortable with your trig functions on the unit circle because you are expected to know those values once you're in calculus. If you don't have your unit circle fully memorized, now is the time to make sure you get that memorized. You're really going to need it in Calc 1, Calc 2, and beyond. Let's go ahead and start plugging in this pi and see what happens. I will get pi times cosine of pi. Now cosine of pi is on your unit circle and it happens to be equal to -1. So I get pi times -1, which is -pi. All right, so all three of these examples worked perfectly fine just by plugging the number in. Now, don't get too excited because not all limits work that way. You can only use direct substitution when your function is continuous at your a value. If it's continuous at that a value, direct substitution works and it's straightforward and everything is nice. But that doesn't always happen. So our next examples, we're going to start having some issues arise, and we're going to learn some different techniques to try to figure out how to still calculate the limit algebraically. So our next example, let's try to do the limit as x approaches 1 of x squared minus 1 over x minus 1. Now remember, the first thing you should always try to do is try direct substitution, because it usually doesn't take too long to try that, and if it works, then you're finished. So what would happen if I were to plug this 1 in? If I were to plug the 1 in, we would get on top 1 squared minus 1, which is 0. And on the bottom, I get 1 minus 1, which is 0. And that's a problem. We don't want to have division by 0. We have no idea what 0 over 0 is. It's an indeterminate form. So we need to do something different to calculate this limit. Anytime you get a 0 over 0 situation, that should be a big cue to you to use algebra. What type of algebra you use depends on the particular problem, but usually it's pretty clear what you should try. If I were to ask you what kind of algebra I could try to do to simplify this problem, you might think about factoring, because the numerator factors. And that is exactly the technique I'm going to use here. So factoring is one technique that you should try when you get a 0 over 0 situation. So let's try to factor this. On the top, I have a difference of squares. X squared minus 1 factors as an x minus 1 and an x plus 1. My denominator is still x minus 1. Now we should look and see, can this simplify? Do I have any like factors that can cancel out? And we do. The x minus 1 on top and the x minus 1 in the denominator can cancel out. So I can reduce this limit to the limit as x approaches 1 of x plus 1. After you've done some algebra and simplified, now you should try direct substitution again. So if I plug this 1 in now, I get 1 plus 1, which is 2, and that is the answer to this problem. So if we were to graph the original function, you would have a hole in your graph when x is equal to 1. But this tells us that as we get closer and closer to where that undefined point is, the y value is getting closer and closer to 2. Now we have a theorem. This theorem says that if f is equal to g when x is not a, then the limit as x approaches a of f is equal to the limit as x approaches a of g if the limit exists. So what this is saying is if two functions agree everywhere except for at x equals a, then they still have the same limits as x approaches a, as long as the limit actually exists. So we're going to use this theorem to do our next example of evaluating a limit. We are going to find the limit as x approaches 1 of the function g, where g of x is a piecewise function. It is equal to x plus 1 if x is not equal to 1, and it's equal to pi if x is equal to 1. So I want to find the limit of this function as we get close to 1. Now remember, a limit of a function as we approach a value is not always the same as the actual function value. We don't want to know exactly what g of 1 is equal to. We want to know what the behavior of our function is as we get closer and closer to x equals 1. So using the last theorem that we just had written down, my limit as x approaches 1 of g is going to equal the limit as x approaches 1 of x plus 1. Because my function g and the function x plus 1 are equal everywhere except for at x equals 1. And that last theorem said that if we have two functions that are equal everywhere except at a, then their limits as x approaches a are the same. So now I just have to calculate this limit, and I get, by direct substitution, 1 plus 1, which is 2. So the limit as x approaches 1 of this piecewise function is 2, even though the actual value g of 1 is equal to pi. All that this means is if I were to graph this function, it would look like our y values are getting closer and closer to 2 as we get closer and closer to x equals 1. But we would have just some random other point at 1 pi. All right, next example. Let's do the limit as h approaches 0 of 3 plus h in parentheses squared minus 9 all over h. So remember, the very first thing you should always try to do is just try the direct substitution and see what happens. If I were to plug h equals 0 into this particular problem, I'm going to get a 3 squared minus 9 over 0, which is 0 over 0. What does it mean when we get a 0 over 0 situation? it means we need to do some algebra. This time, factoring is not going to work. What would be your instinct for what kind of algebra to try on this? Well, I know I can't hear you, but I sure hope that you're saying, hey, maybe we should distribute that. And that is a good idea. This 3 plus h in parentheses squared, let's multiply it out and see what happens. So when I distribute, I'm going to have a limit as h approaches 0 of 3 plus h times 3 plus h is 9 plus 3h plus another 3h plus an h squared. And I still have my minus 9. And this is all over h. Let's combine any like terms that we have. I get a limit as h goes to 0 of 6h plus h squared over h. Now at this point, if I tried to plug in the 0 again, I would still have 0 over 0. And that just means that there's more algebra we have to do. So we already distributed. Now what should we try to do? Well, I noticed that I have an h in common up on the top. Let's see what happens if we factor it out. So on the top, if I factor out an h, then I can cancel that h in the denominator. I can cancel the common factors of h. So now I just have the limit as h approaches 0 of 6 plus h. When I plug that 0 in now, I get 6 plus 0, which is 6. So this particular problem, we had to do a couple different algebra tricks. We had to distribute and we had to factor afterwards. That's okay. Sometimes you have to try lots of different algebra tricks to figure out what works. Let's do another one. Next example, we have a limit as t approaches 0 of the square root of t squared plus 9 minus 3, all divided by t squared. So if I were to plug that 0 in at this point, on the bottom, you can see we would have 0 squared, which is 0. On the top, I would have a square root of 9, which is 3, minus 3, which is also 0. 0 over 0 means we need to do algebra. Now, this particular problem, you're not going to have much luck trying to factor or distribute. So what should we do? What we're going to do is we are going to multiply by 1 in a very creative way. Remember, multiplying 1 by 1 doesn't actually change your problem because anything times 1 is itself. But the way I'm going to multiply by 1 is multiplying by the conjugate of the numerator over itself. That's a way of rationalizing the numerator, and it's going to get rid of all of the square roots in the top of this problem. So let's give it a shot. Multiply by the conjugate of the numerator on both the top and the bottom of this problem. So the conjugate, if you remember from pre-calc, is the exact same thing that we have, except you change the sign in the middle. So I'm going to have my square root of t squared plus 9 plus 3 instead of a minus 3. Now, I know that looks really crazy right now, but trust me, this is going to make our lives a lot easier. So on the top, I would suggest you put some parentheses around this to emphasize the fact that we're going to be distributing. And I would suggest that on the bottom, you don't distribute. You just keep it written as t squared times all of that other stuff in parentheses. All right, let's see what happens now when we try to distribute everything on the top of this problem. So I'm going to have a limit as t goes to 0. Let me fill in my denominator so I don't forget that it's there. And let's see what happens when I distribute all of that stuff up in the top. So this square root times that square root, it has the same stuff underneath the root, so it's a square root times itself. It undoes the square root. I'm just going to get t squared plus 9 for that first multiplication. Now I have this square root times 3, so that's plus 3 square root t squared plus 9. Now I have to do a minus 3 times the square root. So minus 3 square root t squared plus 9. And then to finish it up, I have my minus 3 times 3, which is minus 9. And now you can see a little bit of the magic of multiplying by the conjugate. Notice what happens to those middle terms there. I have a positive 3 square root of t squared plus 9 and a minus 3 square root of t squared plus 9. So they subtract away to 0, and I won't have any square roots left on the top. I'm just going to have t squared plus 9 minus 9. So when I combine all of my like terms on the top, it simplifies to just a t squared on the top. So we get that this is equal to the limit as t approaches 0 of t squared on top over t squared times square root of t squared plus 9 plus 3. And this is why I said to not distribute the denominator, because most of the time, not always, but most of the time, you will now get some cancellation. I have a t squared on top, which cancels the factor of t squared on the bottom. And so now I can rewrite this limit as the limit as t approaches 0 of 1 over square root of t squared plus 9 plus 3. Now that we've done all of that simplification, it's time to try to plug that number in again with direct substitution. Let's see what happens. When I plug this 0 in, I get 1 over square root 0 squared plus 9 plus 3. 0 squared plus 9 is 9. Square root of 9 is 3. So I get 1 over 3 plus 3, which is 1/6. So that was a good example of how multiplying by the conjugate to either rationalize a numerator or a denominator can help you find your problems. So the hardest thing about evaluating limits is deciding, well, which algebraic technique do I need to use? And unfortunately, that's something that can't really be taught. I'm trying to give you all the suggestions I can through this video, but a lot of it's just going to come from practice and building your own intuition on which techniques to try. So we've already talked about the techniques of factoring, distributing, multiplying by a conjugate. Those are the most common things to try. So now we're going to learn a very, very special theorem that can help us calculate some rather complicated limits. This theorem is called the Squeeze Theorem. And the Squeeze Theorem says, if f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a, except possibly at A. And if the limit as x approaches A of f of x equals the limit as x approaches A of h of x, and we'll just say that equals some number L, then the limit as x approaches A of g of x is also L. So what is this saying? This is saying if we have three functions that are kind of nested inside of each other, and the limit of the lowest function and the highest function are equal, well then the limit of the function smushed in the middle has to also equal the same thing. That's why it's called the squeeze theorem, because we're squeezing that middle function in between the other two, and then we can calculate the limit of that middle function. I'm going to quick draw a diagram representing what this squeeze theorem is saying, because it's a little difficult to look at all of the symbols and understand what it's saying, but with a picture, it actually makes quite a bit of sense. So here's just a generic drawing. We'll say there's A, and we'll say this is L. And I'm going to draw my three functions, f, g, and h. So I'm going to just have h, we'll just have h do something like this. And let's have f be down here. Here's f. And then let's have our g be smushed in the middle. And I'm going to make my g look really, really complicated. So let's say this is g. So my function g is very, very complicated, but it's always in between the functions f and h. And we know that the limit as we approach A of h and the limit as we approach A of f is equal to this value L. And notice how it smushes my g to that same exact limit in the middle. You can think of it kind of like a sandwich, and you just pinch the sandwich in the middle. They all have to equal at that same point. All right, let's do an example using the squeeze theorem. So we're going to use the squeeze theorem to evaluate a limit. We're going to show that the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. So let's take a look right now. If I tried to do direct substitution on this, I would have a 0 squared times a sine of 1 over 0. 1 over 0, we can't divide by 0. We don't know how to evaluate this. And looking at this particular limit, factoring is not going to help. Nothing I can distribute. There's not even a conjugate to multiply by. So we're kind of stuck without having any algebra techniques to try. This is where the squeeze theorem comes in handy. What do we know about our trig function sine? We know that no matter what is plugged into sine, you're going to get a result that's between -1 and +1. So what we know that -1 is going to be less than or equal to sine of 1 over x, which is less than or equal to 1, because our sine function is always between -1 and 1. And from here, okay, that tells me about sine of 1 over x, but my function is x squared times that. So let's multiply everything in this inequality by x squared. I get negative x squared is less than or equal to x squared times sine of 1 over x, which is less than or equal to x squared. I don't have to worry about flipping any of my inequality signs because x squared is always going to be positive. So we're not multiplying or dividing by a negative. So what this tells me is the function that I care about is smushed in between these two functions, negative x squared and positive x squared. So by the squeeze theorem, if I can show that the limit of the negative x squared equals the limit of the positive x squared as x approaches 0, well then that middle function is going to have the same exact limit. So let's see what those two limits are equal to. The limit as x approaches 0 of negative x squared, if I just plug it in with direct substitution, I get negative 0 squared, which is 0. And if I plug it into the biggest function, limit as x approaches 0 of positive x squared, again, just use direct substitution, you get 0 squared equals 0. So I have the limit of both the smallest function and the biggest function equaling each other. Both of those limits are equal to 0. This means by the squeeze theorem that the limit of the function smushed in the middle has to also be 0. So by the squeeze theorem, the limit as x approaches 0 of x squared sine of 1 over x is also equal to 0. That's pretty cool. All right, so now I need to give you one fact that could also be proved using the squeeze theorem, but I'm not going to prove it in this video. I'm going to give you a fact that comes up an awful lot when trying to calculate some limits, and you can just use that fact each time you have that sort of situation. And then we're going to do a couple of examples using that fact, and that will be it for this video. So here's an interesting fact for you. The limit as theta approaches 0 of sine of theta over theta is equal to 1. And we also have that the limit as theta approaches 0 of theta over sine of theta is equal to 1. So all that this is saying for an intuitive purpose here is that when we get really, really close to 0, the angle and the sine of the angle are very, very close to each other. So you end up getting a ratio that gets closer and closer to 1. This fact is used all the time in calculating limits. And I'm going to do our first example using this fact now. So here's a good example. Let's find the limit as x approaches 0, sine of 7x over 4x. So if I were to try direct substitution on this problem, I would plug in that 0 and get sine of 0, which is 0, over 4 times 0, which is also 0. So that's your clue that there's something else we can do. And we are going to use algebra to finish this problem up. We're going to use algebra and that fact we just learned. That fact that we had just learned says that when you have sine of something divided by that same something, and your limit is going to 0, then you get 1. So this limit is not equal to 1 because right now, this 7x inside the parentheses does not quite match that 4x. They both have an x, but the numbers disagree. So I'm going to multiply by 1 in an interesting way so that I can use my fact. In order to use my fact, I really need to have a 7x in the denominator to match the 7x in the parentheses. So what I'm going to do is I'm going to multiply this by 1, but I'm going to write 1 as 7 over 7 because I really need that 7 in the denominator so that I can use my fact. Now, we know that in the real number system that multiplication is commutative. It doesn't matter which way we write it. So I'm going to rearrange this a little bit as the limit as x approaches 0 of sine of 7x over 7x times 7 over 4. So I rearranged in the denominator because 4x times 7 is the same thing as 7x times 4. They would both give me 28x. But now that I've written it this way, it becomes very clear how I can use my fact because I know that the limit of this guy, sine of 7x over 7x, that goes to 1 by my fact. So the entire limit is equal to 1 times the 7/4, and I just get 7/4 as my final answer. Good. We're going to do another example where we have to do something like this to use the same fact, but it's going to be a little bit more complicated. So I hope you know some of your trig identities. Luckily, the trig identity we need happens to be the most popular one, so I hope you know it. But you should brush up on your trig identities if you don't feel confident in them. So our last example, we are going to find the limit as theta goes to 0 of cosine of theta minus 1 over theta. So if we take a look at this problem right now and think about plugging that 0 in, cosine of 0 is 1. So my top is 1 minus 1, which is 0. The denominator would be 0 as well, so I have 0 over 0. This means we have to be able to do some algebra to finish this up. I can't use the fact that I just learned because I don't even have a sign in the problem right now. So what can we do? Well, there's no factoring to be done. There's no distributing to be done. So let's try like multiplying by a conjugate like we did on that other problem. Let's see what happens if I have limit as theta goes to 0, cosine of theta minus 1 over theta times the conjugate of the numerator over itself. So remember, since I'm multiplying by 1, I'm not actually changing my problem in any way. And like that previous problem where we multiplied by a conjugate, we will distribute everything on the top, but we'll leave the denominator not distributed. Let's just see what happens. So I'm going to have a limit as theta goes to 0. My denominator is theta times cosine of theta plus 1. And in the numerator, I get cosine theta times cosine theta. That's cosine squared of theta. Then I would have cosine theta times 1 and a cosine theta times minus 1. They're going to subtract away. And then my last term is minus 1 times 1, which is minus 1. So right now you might be thinking, well, we're not really any further along on this problem. If I plug in that 0, I still have 0 over 0. This is where our trig identities come in. What is your favorite trig identity? Probably sine squared plus cosine squared is 1. So I have a cosine squared here. Cosine squared would then be equal to 1 minus sine squared. So I'm going to use that trig identity. Cosine squared is 1 minus sine squared to rewrite this problem. Using that trig identity, I get the limit as theta goes to 0 of 1 minus sine squared of theta minus 1 all over theta times cosine of theta plus 1. And you can see on the top, the 1 and the minus 1 subtract away. So we just have a limit as theta goes to 0 of negative sine squared theta over theta times cosine of theta plus 1. And at this point, if I try direct substitution, I'm still stuck. I still get 0 over 0, but we're getting super close to having the answer now. We're going to use that fact that we learned about the limit of sine of theta over theta. So first, let's rewrite this a little bit. This limit is equal to the limit as theta goes to 0 of sine theta over theta times a negative sine theta over cosine of theta plus 1. So all that I did there is rewrote this as a product. Remember, the limit of a product is equal to the product of the limits. So what happens now when I take these limits? The limit of this guy is going to be 1, using that fact that we learned. To find the limit of the other guy, we would just plug in 0 for theta and see what happens. So when I do that, I get my limit of the sine theta over theta is 1. And the limit of this other piece of my product, I get negative sine of 0 over cosine of 0 plus 1. So what is that equal to? Well, sine of 0 is 0. Cosine of 0 is 1. So I get 1 times a 0 over 2, which this is just equal to 0. So that was a lot of work just to get an answer of 0, but it shows you how using this fact, as well as using trig identities and algebra tricks, can help you evaluate some limits. So that's all I have for you today. I hope you get lots of good practice in using your algebra tricks to evaluate some limits. And in the next video, we're going to talk about limits that involve infinity. And so it should be a pretty good time. And I will see you on that next video. If you have questions, drop them below. Or if you're a current student, feel free to email or attend office hours, and I'll help you as quickly as I can.